In this video, we're going to talk about building exponential, logarithmic, and logistic models from data. As you could probably tell, I'm using a kind of different screen recording, and the audio might not be the best, so I apologize if this video is more brutal to get through than normal. But we're going to be using our graphing calculator to do all of these things, so if you want to pause this and grab your graphing calculator, I would highly recommend. So we're going to be inputting data sets, so statistical analysis is happening here. So we're going to be looking at scatter diagrams. So before we even input any data, we need to know what exponential, logarithmic, and logistic scatter diagrams can and will look like. So the first two are exponentials. So if I have exponential growth, it's going to look like this. You've seen exponential graphs plenty. And then if it's exponential decay, it's going to look like this. Keep in mind that exponential graphs can and will cross the y-axis. And that's different from log graphs or scatter plots, is that the y-axis is our vertical asymptote in most log cases. So our log graph could look like an exponential a little bit. The only two that could be confusing are these two, but a log scatter diagram will not cross the y-axis and usually just hangs out in that very first quadrant. Where an exponential will hang out in quadrants 1 and 2 because it wants to, and it can. And then a log kind of growth equation looks like this, which is very different from exponential scatter diagrams. And then the last one, which I feel like is the most unique and hardest to mess up, is the logistic curve. That's that weird S curve because of carrying capacity. So we want to keep these in mind when we look at scatter diagrams to figure out, do I use exponential regression, logarithmic regression, or logistic regression? Because obviously that's going to matter. All right, let's look at an example. So our lovely friend Kathleen, I'm sure you all have a friend Kathleen, is looking to find an equation that will model the growth of cell phone usage in the United States. She starts in 1985 and ends her data set in 2008. Some good years in there, if I do say so. So what she's collected is the years. So that's going to be our X or L1 column. But she's going to start in 1985 and she's going to make that X equals 1, year 1 where she was collecting data. So that means 2008 represents 24. So she's going to enter 1 through 24 here, which is also what we're going to do. And then in our Y column or L2 column is the number of subscribers in millions. So that shouldn't shock you that in 1985, not even 1/3 of a million folks had a cell phone, because why would you? But in 2008, 270 and 1/3 million folks have cell phones, and that's only the United States. So what we're going to do is we're going to go through the process of entering it in our calculator and then finding all the things. To me right now, before I even read the rest of the problem, I'm thinking this is probably exponential growth because I happen to know that technology grew exponentially from the 80s till the 2000s, but we'll see. So the first thing that I want to do is hit the stat button, and I'm going to hit enter, and I'm going to edit those lists like we did with linear regression. So I'm going to enter 1 through 24 over here, and then all of these Y inputs. I've already done it because it takes literally forever on this emulator, so cut out some of that time. And then in order to look at the scatter diagram, I'm going to go second Y equals. And so I want to make sure that my first stat plot is on. Mine is, but if it wasn't, it would look like this. The off would be selected, so all you do is hit enter, and page over, and hit on. Wow. So when I hit graph, it creates this graph. Now, if your graph looks like this, when you hit graph and you've got the Y and the X axes here, and you're like, whoa, that don't look right. So how you get from here to the graph that you want is you go to zoom and you hit number 9, and that's zoom stat, and it'll bring you here. And if you want to go back to the XY, it's zoom 6, which is zoom standard. So looking at this, I see, this happens to look like this exponential curve here. It's definitely not a log or logistic, so it's exponential growth, which we guessed because technology. So the next thing that I want to do is I want to find the equation, and I don't need to just make up numbers because, well, that won't go well. We hit stat, and we move over to our calc menu, we're going to go down until we see something that resembles exponential regression. And that's going to be expreg, which stands for exponential regression. So if you remember back to when we did linear regression, this is very much the same. Your calculator screen might be slightly different. In class, I'm happy to help you figure out how to do this if yours doesn't look like this list. So X list is L1, Y list is L2. Again, if yours are in different places, let me know. Happy to show you how to change that. We don't need to worry about the frequency list right now, but we've got store regression equation. And I want to do that because the numbers are going to be long and I don't want to type them out myself because I'm lazy. So we hit vars, page over to y vars, function. I want number 1, and then I'm going to calculate it. Give it a moment. All right, so y is equal to a times b to the x. So that is a traditional exponential equation. Not necessarily the one that we're used to seeing. We're used to continuously compounding for financials or exponential growth or decay, and that's PERT, right? Where a is the amount, and that's equal to our principal or our starting amount times e to the RT, or our rate times time. So we're missing that time as our variable, which is the x. So I'll show you how to work that out in just a moment. But our starting amount is 0.8649, yada, yada. And then our b to the x value is 1.318, yada, yada. So how do I get y equals a b to the x, which is what I have here? This is the same screen, except it has the r values, which you can ignore. So these two screens are the same. Why they're there twice? Nah, fun times. And I want it in this PERT equation. So remember, you can have A and A naught. A naught is your starting amount and your principal. And K in this situation is our rate. So whether or not you like PERT or you like this A naught, KT thing, doesn't matter. So the only thing that's really different here is that, first of all, I have A naught, which is like our principal. That's our A value. That's going to stay A. But remember, our b to the x is b to the 1.318. But in our PERT equation, it's e, which is a totally different number, to the RT, or rate, or k times t. So what I do is I'm like, all right, b to the x, this thing here, is the same as the e k to the t. So if b to the x is 1.318, that means that e to the kt has to be equal to that 1.318. But e is not 1.3, which is the problem. So I know that if b to the x is that 1.3 to the x, we know that if b is e to the k, that means that b and e to the k are the same thing, 1.31855, that thing here. So if I take the ln of both sides, if I take the ln of e to the k and ln of 1.31855, remember the ln and the e's, they cancel, so I'm just left with k. So k, this e to the k, is equal to ln of that b number. So really, just take ln of b, and that becomes your rate. That's all that I'm saying. This a and that a are the same. And then e to the kt is e to the ln of b. So ln of b is 0.2765, which is the rate of growth. So this thing exponentially grows at a rate of 27.65%, continuously compounding. Wild technology. It's so crazy. So that is interpreting the k, or the rate, in that part. So the last thing that we can actually do is we can predict. So Kathleen, goodness bless her, right? She only stopped at 2008. But let's make a prediction. What do we think the cell phone usage could be in 2009, or even today in 2022, which you can tell I'm recording in 2022. So what we can do here is, because we stored the regression equation, genius on our part, we can go to a table and look at 2009, which would be 25. So my table started at 25. So remember our little cheeky how to get there quick little hint. I don't know. Words are hard. You go to second window, which is table set. And let's say I wanted to start at 25 or 35 or 40 or whatever you want. You put it there. And then you go second graph, which gives you your table. So in 2009, we could predict that roughly 869.8 7 million people were using cell phones. Wow. And now let's look at a second example. So let's say our other friend, Jody, who's a meteorologist, go Jody, she's interested in finding a function that explains the relation between the height of a weather balloon in kilometers from the ground and the atmospheric pressure, which is measured in millimeters of mercury on the balloon, whatever that means. She collects the data as we see here. So the atmospheric pressure is going to be our L1. Again, I've already entered that in. Also, fun fact, if you want to clear a list, you go all the way up to whatever it is, L1, L2, L3, you hit clear and then enter, and it'll eliminate all the stuff from that list. Not going to do that now because that would suck for me. So I have all of my X values listed, and then I have all of my Y values listed, and I've double checked them because, if you get your numbers wrong, your whole data set is a little skewed. Not fun. So my stat plot is on. Great. Gonna graph it. Should already be, oh, there we go. Should already be in Zoom stat. So remember Zoom number 9, that gives you to Zoom stat. So this almost looks like a linear regression or a line, but it closely matches a logarithmic decline here. It's not going to be exponential decay because it doesn't have a swoosh, like a really quick drop. Plus, it's really far from the y-axis, which is over here. So that makes me think it's logarithmic. So we used a graphing utility, made the scatter diagram. We know, well, she told us it's a logarithmic model, but we could figure it out ourselves with our own brains. And so let's calculate. So stat, calc. And then the only one that's logarithmic in our calculators, it's not linreg, it's going to be lnreg, which remember is the natural logarithm. So that's the one I'm going to pick, L1, L2. Going to store it, vars, y vars. I'm going to have it replace my current one that's in there, and then hit calculate. Here we go. So our our logarithmic regression or natural log is going to be a plus b times ln of x. So a is 45.7 and b is negative 6.9. So that's going to be my equation. And luckily for us, we don't have to manipulate any of the numbers or apply ln or any of that stuff that we did to the exponential equation because logarithms are straight up what they are. So that's going to be our equation, and we can do a lot with that. But let's say that Jody, lovely Jody, wants to predict the height of the weather balloon if the atmospheric pressure is 560 millimeters of mercury. So that means that X is 560. So again, I could go over to my table. That's still at 25, but I want it to go to 560. All right, big numbers. And so when I do that, I get about 2.108 roughly kilometers, which is exciting. All right, and the last example, this one doesn't have quite enough of a backstory for me to feel something for it, but we're going to continue. Let's say a scientist is collecting the amount of yeast biomass in a culture after T hours. I don't know what the unit on the biomass is, so just pretend. Or if you know a scientist that studies this stuff, ask them what the unit is. Is it grams, micrograms? I don't know. But anyway, this lovely scientist recorded the yeast biomass from time 0, so at the start, till the end at 18 hours. So we're going to do what we've been doing, and that is enter in this data. So I'm going to enter in our edit list. I already put the stuff there, checked it over. And so let's pretend we don't know it's a logistic function. And let's make sure our stat plot's on. Great, it's on. And let's go to graph. Woo! And remember, if this doesn't quite show up, you go to Zoom 9 and Zoom stat. That's a logistic function. That's that beautiful, weird looking S curve. Gotta love it. So that means in order to find the equation, I'm going to go over to stat and then calc. And then there's only one logistic option, which is logistic. And that's B on mine, at least. And so going to do the same stuff, L1, L2, store equation, vars, y vars, going to replace the first one and go down to calculate. So I will be honest, my calculator here took a very long time and it looks like it's still taking a very long time. So here's what the answers will be once they pop up. So it's going to be C all over this thing in the bottom, because we know what a logistic function equation looks like. It's a crazy looking fraction. So C is this number, 663, which is our carrying capacity. And then 1 plus A, which is 71.57. Oh, there she is. E to the negative B, so negative 5.469, yada, yada, X. So those are all of our numbers. There's no other way to write that equation. So once that's in there, we can also analyze predicted carrying capacity of the culture. Sorry, not of the future. Ooh. Carrying capacity, we know, is the C value up top, so 663, whatever the units is for the yeast biomass. Ooh, it got really close. It got really close after T equals 18. So let's see how much it would be at 19 hours. So if I stored that equation, it's in there. I'm going to graph it. See that beautiful curve? Oh, that's a nice curve. You know you're a math nerd when that makes you happy. And then we can look at the table of values. So let's say I was looking at 19 hours. Do not want 560. But look, even at 560, it's 663 because that's the carrying capacity. Huzzah. Let's start at 19 and find out what I will get. I'll get about 661.5 or 0.6 units of the yeast biomass. And that's also exciting. So you can do a lot. Also, take a look at the scatter diagrams before you automatically assume that it's exponential, logarithmic, or logistic, or if the problem tells you what it is, then, well, great, use that. But it's been a wild ride. Thank you for coming along with me on this journey. Let's hope that this works out and you see it and I don't have to redo it. So thank you for watching.